The last topic in this chapter is charging and discharging a capacitor through a resistor. This is called an RC circuit, R for resistor, C for capacitor. This is more realistic than what we've had so far when we talk about charging capacitors because there's always at least the battery's own internal resistance in the circuit. So in these figures we have a battery, a resistor, a capacitor, and a switch. In the A position, the battery charges the capacitor, but the current to charge it is limited by the resistor. We can use Kirchhoff's laws to figure out what the charging current is by analyzing this middle figure, what we would get with the switch in the A position. The battery's EMF is this epsilon, and if we go around clockwise, we get epsilon minus IR minus whatever the voltage is across the capacitor. Well, we actually know voltage on a capacitor, Q equals CV, so V is Q over C. So we can write the equation like this. This looks like regular old algebra, but the problem is if we put in what I really stands for, which is delta Q delta T, we see this is a special kind of equation. It's actually a differential equation, which is way beyond what we're going to require math-wise. So you don't need to know how to solve it. But one thing to notice about it is important. You've got both charge here and change in charge over time here. And when you see both of those things in an equation, that suggests you're going to have an exponential function involved. So the charge on this capacitor is a function of time. If we have somebody solve this differential equation for us, it's going to look like this. Q is a function of time, doesn't matter, big Q, little q, is capacitance times battery EMF times this factor, 1 minus E to the T over RC. We could also write the voltage across the capacitor instead of the charge. We would just use V equals Q over C. V as a function of time is this same thing over C. Now the exponent of E has T divided by RC. That tells us right away RC must have units of seconds because we can't have any units in an exponent. We have to have seconds over seconds here so that they go away. This RC is called the capacitive time constant. Sometimes we use a Greek tau with a little c to represent that. If we plot what this looks like as a function of time, it's this. It starts off going up very quickly and then flattens out and only asymptotically reaches the final battery voltage. So in theory, it would take an infinitely long time to get there. After a single time constant, one value of this, whatever this is in seconds, one value of that, we want to know what will the charge on the capacitor be. We use our formula for charge as a function of time. And here, if we use one time constant divided by RC, this is just e to the minus 1. You can plug that in your calculator and see what you get. 1 minus e to the negative 1 is going to be about 0.632. So this means it's 63% of the way to maximum charge after just one time constant. After 5 time constants, we're at 99.3% to maximum charge. If we felt like we had to wait for 10 time constants, we would be essentially completely charged. If you look, that's very, very close to 1. What this means is we don't have to do this complicated math in our heads if we're trying to figure out the state of charge on this capacitor. All we have to do is the much simpler math of R times C. So if we have a 1 microfarad capacitor and a 100 ohm resistor, its time constant is going to be 1/10 of a millisecond, and we know it's going to be 99% charged in about half a millisecond. What about after the capacitor charges if we want to discharge it? That's when we'd move this switch over here to B, and we get this circuit. Notice there's no battery in it. The capacitor is the only thing driving a current. And it's going to drive it right through that resistor and back to the other side to discharge itself. So Kirchhoff's law would then say we get this, the potential drop across the resistor and then the potential of the capacitor. Again, differential equation. It's a little bit simpler this time. And what we get is charge as a function of time is our starting charge times e to the negative t over RC. What does this look like? Well, it drops exponentially towards 0. So as we wait, it will eventually drop down to this. How long would we wait? Well, if we waited 5 time constants, we'd be down to more than 99% discharge, so it would be holding less than 1% of its charge. If we wait 10 time constants, it's way less, like 1,000% of its charge. This is actually a really common lab in an in-person Physics 2 course. You charge up a capacitor and you measure the voltage as a function of time, and you see that it matches this model. There's not an easy way to measure the charge on the capacitor directly, but since we know Q equals CV, we can just measure the voltage on the capacitor and use that to infer the charge. When you're doing this lab, even with intro students who aren't familiar with the equipment, if they are even a little bit careful, they'll get this curve dead on. It'll typically agree, the theory and experiment will agree to within 1% or less. This process is so reliable that the main way to build an electronic clock for many years was to use an RC charging or discharging circuit. The interval wipers in your car that you use when it's raining but not much originally used an RC circuit to time the delay between swipes of the wiper. The little knob at the end of the wiper stalk to make the interval longer or shorter is just a variable resistor. When you change that R, you change the time constant, so you change how long between swipes of the wipers.